Okay, static electricity. To keep it simple, when we see static electricity, we see charge moving from one object to another. And I'm going to jump over to a PhET simulation and explain this a little bit more detail, because this is where we start to get charge transferring from one object to another. And it's lots of fun and really cool. All right, welcome back. In this video, we're going to talk about Coulomb's law. So Coulomb's law is stated, the electric force, Fe, the electric force is K, which is sometimes written Kc because it's Coulomb's constant, or Ke. I've seen it written both ways, and you could call it K. Just know that we use K for other things too, okay? So it's like K is for constant, just kidding. Okay, but that's what it is basically. So this is a universal constant for Coulomb's law, and it's 8.99 times 10 to the 9th power kilograms times meters cubed per second squared times Coulomb squared. If you do all the unit math, what you wind up with is meters per second, kilograms times meters per second squared, which is the same thing as a Newton. Okay. So this is actually equal to, if we do all the math, newtons per Coulomb squared times meters squared. And then if you have your coulombs times coulombs and then meters squared down here, those will cancel out and you're left with the Newton. So, but this is a fixed constant, it doesn't change, and it always goes in here. Substitute for the K. Q1 is the charge of the object. So this could be a proton. This could be an electric fence, the whole wire. It could be all kinds of, what is the charge of that object? So you've taken the balloon and you've rubbed it on your hair, okay? It actually sticks to your hair because it's gained some charge. So we could talk about the charge on the balloon. And we could say that's Q1, the charge of the balloon. Q2 would be the charge of the other object. So it could be another balloon. It could be the charge that's on your hair or the charge on the wall like we looked at in the simulation. And they react to that using this law, using this equation. So the bottom part is the distance between them, and it's from the center of charge. Now, we're going to keep it simple and pretend that everything is a sphere and has a perfect set radius, but like the balloon, it's not perfectly round unless you happen to blow it up that way, okay? So this can get quite a bit more complicated, but it's from the center of charge between the two objects. What's important to notice about this, we've done an equation that looks almost just like this one. What happens to the force, what happens to the answer if I have a really big charge? If I have a really big charge, then the force is going to go up or down, or stay the same. If the charge gets bigger, then the force is going to get bigger. If the charge gets smaller, then the force is going to get smaller. So they're on top of the equation, so it's directly proportional. And as one of these changes, the force will change the same way. All right, so now the tricky one. We're dividing by our squareds, so don't forget squared. We've had to deal with this before. So if the distance doubles, if they get farther apart, we're going to divide by a bigger number that's also squared, so it's even bigger. So when you divide by a big number, then the result is going to be smaller. Okay? When you make the distance closer together, the force is going to get larger because you're dividing by a smaller number. Okay? And if you ever that doesn't quite make sense to you, just do something simple, like go 10 divided by 2 squared. Okay, well, that's going to be 2.5. Okay, I'm just making up the numbers. Okay, so 10. Let's make this be bigger. 3 squared. Well, 3 squared is 9, so that's going to be 1.1 repeating. So the distance got bigger, but the result got smaller, okay? If I go the other way, 10 divided by 1 squared, so they got closer together. 10 divided by 1 is 10. So the force got greatly bigger. So the closer together they get, the force gets bigger. Farther apart they get, the force gets smaller, okay? That's called inversely proportional. So I hinted at it, but you've probably already guessed it. Look at this. Physics is all about looking for patterns. I stated that earlier when we did talk about gravity, but look at this. Force electric, force of gravity. Force of electric charge, we've got a constant, we've got a constant. The numbers are very different, the constants are very, very different, but we have a charge and then we have a mass. We have a charge 2, we have a mass 2. We have a distance squared, we have a distance squared. This pattern has led to patterns like this, not just this one, but patterns like this have led to string theory, okay? So as we're thinking like scientists, we should always be looking for patterns. We should be looking for, hey, wait, that is the same as that. Is there a connection? Sometimes there is, sometimes there isn't. And in this case, we don't know what the connection is, okay? We have some ideas, but we don't know what that connection is. How are they the same thing? That's why string theory has a lot of ideas on how they're connected, but this is the one, there are, of the 4 fundamental forces of nature, this is the one we haven't connected with all the others, okay? Gravity is the one that's the outlier, okay? All righty. What we got to understand, and what's really important about this, is the electric force determines the properties of materials, okay? So atoms are made of protons, neutrons, and electrons, which are charged particles. So if we take sodium and chlorine, for example, when they combine, they will lose and gain electrons so that the sodium becomes positive and the chlorine atom becomes negative. Basically, chlorine picks up an extra electron, sodium picks up loses an electron, doesn't change protons. If it changes protons, it becomes a different element, so it's not sodium anymore. Okay, that's called a nuclear reaction. So the protons don't change, only the electrons ever change from atom to atom. But now sodium has lost an electron and it's positively charged. Chlorine is negatively charged. Opposites attract. And now we've got table salt. Okay, so it's all based on the charge. So 2 atoms stick together and we get sodium chloride or table salt. This electric force is also the reason why your hands don't pass through each other, okay? There's that electric field, if you will, and when your hands collide, it's a combination of the magnetic force and the electric force, but basically it creates a solidity to the atom. Have you ever like taken a magnet and put it over a magnet, or you feel them pushing against each other, okay? And they don't have to be touching. Well, that's actually happening at an atomic level. Okay, to put it very simply. Okay, so the electromagnetic force is responsible for the solidity of matter, okay, because of this interaction between charges based on Coulomb's law. The properties and composition of materials is based on Coulomb's law. So it's super important, especially if you get into any kind of chemical engineering of any kind. All right. That concludes this video series. In our next set of videos, we will be exploring current electricity.